So first, why don't we review a little bit of last time? Uh, okay, Sean, are you with us?
Yes, I am.
Oh, good. Okay. So, Sean, why don't you tell us what K-space is after our last lecture?
I actually looked it up last night, and I'm still not sure what it is, but it 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 should be a place where information is stored between translating in between like a frequency domain and time domain, or space where they keep information before it's translated into the picture.
Yeah,
Um,
right.
and and you feel it at one you feel it again one space at a time, and it covers the entire frequency spectrum that you get from the sequence or from the echo,
So,
and then you can take that information that you've stored.
yeah, you know,
Yeah, well, I was going to say, I didn't know whether you could hear me over the loudspeaker.
yeah,
Then you take that information, you can manipulate it in certain ways, whether you want to take it and apply the Fourier transform and like take the center out, or take the periphery out, or take half of it out, or you can use the information that's stored in there to create images in different ways.
yeah. So the bottom line is when we acquire data from the patient, what we're receiving is electrical signal. And what we do by doing the frequency encoding, phase encoding, and slice encoding gradients is we're able to take the energy in that electrical signal and determining which voxel it's coming from. Now, what we're actually receiving is that electrical signal. And what we then store is the strength of the electrical signal. So K-space is really a three-dimensional array of signal intensities from what we've received from the electrical impulse that comes in the wire from the person's body. So it comes in as an analog signal. We digitize that, and then by using the different gradients, we're able to take the segments of energy that are associated with the different voxels and store that in that signal intensity. And that really gives us, that's how we fill K-space. And using standard imaging, what we do is we fill one line of K-space at a time. We can get one line because if you remember, first we use a slice encoded gradient, so we're only dealing with a single slice using standard old-fashioned spin echo imaging. Then we do a 90-degree pulse, 180-degree pulse. In between the 90 and 180-degree pulse, we have a single phase encoding. Then we wait until we get the echo back, and we'll talk a little bit more about how the echo is generated in subsequent lectures. When the echo comes back, we put on a gradient so that we spread out the signal in that echo along one direction based upon frequency. Then when it comes in, we take chunks of each frequency and store that signal intensity separately. So the chunk of signal intensity at the far, let's say, right side of the body is stored right here. Let's say the first 100 kilohertz. It depends upon what our matrix size is and what our bandwidth is. So the number of kilohertz in this bin is just going to be the bandwidth divided by our matrix size in that direction. The higher the matrix size, the higher the spatial resolution. So we bend the energy into separate bins, so these are all numbers. They're signal intensities associated with that frequency band that we tag uh, uh, in the frequency encoded direction. So with one 90-degree pulse, we then fill one line of K-space. Then what we do is we wait a TR, we do another 90-degree pulse, and we fill the next line of K-space. And we keep doing that with changing the phase encoded gradient until we completely fill K-space. So in the old days, we'd do like a 192 by 256 matrix. The 256 matrix you kind of get more or less for free. It doesn't take you any time to increase the matrix size in the frequency encoded direction because we're receiving that all at once. but it does take time in the phase encoded direction because for each phase encoding, you have to wait another TR to change the phase encoding and grab more lines of K-space using standard old-fashioned spin echo imaging, which we'll understand first, and then we'll understand modern techniques in a little bit. And then we can fill K-space, and if it's a 192 by 256 matrix, which is typically what we did in those days, then we would do 192 different phase encodings in the phase encoded direction. And if we needed more signal to noise, we'd do it twice and average them together. And so that would typically, it would come out with about a 17-minute scan if the TR was around 2000. So that was the old days. But once we fill all these numbers in this matrix, then we can uh, uh, use Fourier transform to transform from K-space into image space. But this is the data that you actually get on that electrical wire coming from the receiver coil. Okay, that's probably still
So
clear.
where does that data live? Is it like on a chip or something?
Yeah, it lives in the memory of the
Dr.
computer.
Cruz?
It lives in the memory of the computer.
Okay.
So as we saw last time, this is typically what K-space would look like. It tends to cluster around the center of K-space, which is around a frequency close to zero. This would be high positive phase encoding. This would be high negative phase encoding. This would be low frequency encoding. This would be high frequency encoding. Then when you do the Fourier transform in 2 dimensions, you can then end up with the data in image space over here to the right. Now, what's wrong with this image? This
So
really
Dr.
looks
Cruz,
like a bullseye, but what's wrong with this image is that this is only a couple of lines of K-space around the center of K-space. And this is what it should look like if you go ahead and fill out all of K-space. So this is what an image would look like if we just took just the center area of K-space right here, and you get no spatial resolution. All the spatial resolution is in the periphery of K-space. When you add the peripheral information, then you can get a real image. And we talked a little bit about this when we just looked at the one-dimensional, or when we talked about the beaker of water last time.
Dr. Cruz,
Yes,
when you go back to those K-space maps, the one
yes,
thing I don't quite understand is if you're taking information and putting it line by line, which should correspond to the image, why
yes.
does the map look so uniform as opposed to just a non-uniform map of areas of bright, you know,
You mean
increased signal, decreased signal?
you mean why does it look so uniform in the periphery?
Yeah, as opposed to like why isn't it just like random corresponding somewhat to the picture, that you're
Okay.
going to create?
Well, remember, these are mathematically they're equivalent, but they're in 2 different mathematical representations.
Right,
So actually the data is equivalent here, but it's like it's in a different language. So
right. So
this
you just
is
can't
this
make a
is
one to
saying
one.
hello in Mexican, and this is saying hello in English. And if you
Right.
understand only English, then you can only understand this. But if you actually knew Spanish, then you could actually figure out what this was. But it's very hard for human beings to look at this image and know that this is what they're looking at. So it's virtually impossible to train a human to be able to interpret K-space information. And that's why we transform it into image space, which is something we're used to in everyday life. Now, when you do that, what you find out is that this image has many more low frequency information in it than it has high frequency information. All the information around the periphery here is very high frequency information. But if you actually look at this image, there are actually very few interfaces that are sharp. Most of the image is rather bland signal intensity. It's all bright in here in the white matter. There are large areas of gray matter here. The actual percentage of the pixels that are at high gradients and signal intensity are actually very small. And that's why the periphery of K-space doesn't seem to have a lot of data in it. Uh, so the center of K-space is very important for contrast. The periphery of K-space is very important for spatial resolution. If you had if you had an image here that was completely filled with very high gradients of signal intensity, then you'd have a lot more information in the periphery of K-space. But this is very typical of the way K-space would look for almost all the data we have. And the way in which we do a lot of fast imaging uses the fact that this is what K-space looks like. In particular, if there's no motion in the image, the top half of K-space is the mirror image of the bottom half. So what this data is actually showing is that one way you can speed the acquisition of your image is only acquire the top of K-space, then mathematically reproduce it here at the bottom again, then Fourier transform that, and you'll get the image to the right. That's what they did here. They only took half of K-space. They then mathematically duplicated the bottom, so it was exactly a mirror image of the top, did the Fourier transform, and this is what it looks like. Looks very similar to the top one. But if you look here, this is noisier. And what happens when you acquire only half of K-space is that you lose a square root of 2 in signal to noise. So this image and that image are pretty much identical, except this is a noisier image down here at the bottom. If you had a vessel in it, then you'd have a lot of artifact down here, because once you have motion, the top and the bottom of K-space are no longer identical. And pretty much the right and left part of K-space are similar too, but you get a lot more artifact if you try to mirror it that way. All right? Did that answer your question, John?
Yes, thank you. Yes, thank you. Yes.
Okay, so we know what's wrong with that. Now, the next thing I want to talk about is the thing called aliasing. And what happens is if you use too small a field of view on an object, if you if you're not careful, what you'll get is that the right side of the object will be folded back onto the left side. The left side of the object will be folded to the right side, and you'll have an image. The classic image would be a brain where the nose is stuck into the occiput. You've all probably seen that before. So what causes this? And it's generally most marked in the uh, phase encoded direction. So Yuri, what does the term aliasing mean?
Uh, I thought it's kind of similar to wraparound,
Yeah, this is wraparound.
where
Same thing.
where part of the image gets gets tagged to a non-anatomical part, but I'm not sure how to explain it mathematically.
Okay. Let me try an example that may be a little bit easier to start with.
Okay.
How many of you have how many of you have not seen old-fashioned cowboy movies where they start up the buckboard and you watch the wheels, and initially the wheels start going forward, and then it looks like they reverse direction, and then as it gets faster, it looks like they start going forward again. Has everyone seen that in a movie? Okay, Sheila, what causes
Yes.
that?
The speed, like they're this like the movie or whatever, the image can't compensate for like the speed of the moving wheel. So because it's sampling, it's above the like the velocities or something are outside the realm of what we're imaging. So it's like the velocities are outside, um, because
Well, you're right, but let's go a little further. What happens then? Let's say you have a movie, and whenever you do a movie, what you're doing is taking individual images very rapidly, and then when you play them in rapid succession. So let's say you take a snapshot take a snapshot 30 times a second, and then when you play the movie back, you flip those images up 30 times a second, and it looks like a motion moving a movie, right? That's the way movies work. But if you take a wheel with spokes and it moves slowly, then every 30th of every 1/30th of a second, the spoke will move a little bit and you'll see it moving forward in time. But what happens once it gets pretty fast, what happens is a, a spoke in one position will move not just a little bit forward, but it will move almost to where it catches up in a 30th of a second to where the next spoke was located at the original snapshot. So at time t equals 0, you'll have an image of a wheel with spokes. The next frame, if it's going fast enough, one spoke will be almost up but not quite to the position of the previous spoke. And then at the next one, it will move up almost to the next spoke again. So what happens when you play it over time, uh, it actually looks like the spoke's moving backwards, when in reality what's happening is it's not moving backward, it's still going forward. It's just that one spoke has moved forward, so with the next image, it looks like it's a little behind where the next spoke was, and therefore your eyes will see it as the spoke going backwards over time. And then when it gets fast enough again, one spoke will go far enough forward before the next image is taken, so it passes where the next spoke was, and therefore over time it looks like the spoke's now going forward again. So that's just an illusion, because your resolution in time is one 30th of a second. If you started taking the images 1/60th of a second, then you would find you'd have to go twice as fast before you started seeing the aliasing effect. And if you uh, took images very, very rapidly, you would never see the aliasing effect. So it comes from the fact that our images are only once every 30th of a second, and as the wheel speeds up in time, one spoke is in that time period is able to move almost to where the next spoke was, and the illusion then is it's going backwards. So what's happening in an MR scanner is that if we have a field of view that's between these two dotted lines, and that's where our bandwidth occurs, and we put in a gradient, it turns out that in between these lines, our phase encoding, each point will have a unique phase encoding as we go through all the sequences. They'll be able to uniquely be differentiated based upon phase encodings. But if your field of view is small enough, it turns out that if you do the mathematics, any point right here will have the exact phase encoding of a point right over here on the other side of the dotted line. And therefore, the computer will think that anything in this location is actually located here. And therefore, it mismaps it onto the other side of the body. If you increase the field of view, which means you increase the bandwidth and or frequency or spacing of uh, the phase encoding, then is what happens is you'll widen this, and everything in between the lines will have a unique phase encoding, and you won't get the wraparound artifact. And unfortunately, I'm missing some images there. So this is one example of wraparound artifact. This is phase encoding in two directions, and what we have here is the proximal radius is wrapping around the distal radius from bottom to up, and it's obscuring the distal radius because this is all wraparound artifact coming from the muscle tissue proximal to the wrist in this location. So that's all, and then we also have some wraparound artifact from the skin on this side wrapping around over there. So that can produce a lot of artifact, and in this case it obscures our ability to see the scaphoid here, because wraparound artifact is right over the scaphoid. And then this brings us to and I'll talk a little bit when we talk about uh, uh, different ways to accelerate scan times. We'll come back and talk in more detail about the relationship between phase encoding, field of view, and wraparound artifacts. So we're going to come back to that. This was just a beginning introduction to the topic. So let's move on to chemical shift artifact type 2. So Sean, what was chemical shift artifact type 1?
In chemical shift, the protons were shielded by the electron cloud, and it slightly changed um, the it slightly changed the rotation, and therefore it mapped them in slightly different places.
Yeah, so within FAT, deep inside FAT, the
FAT.
magnetic field is actually lower than it is in adjacent water. And since we map things in the frequency direction based upon the frequency, and the frequency is determined by the exact magnetic field, FAT is shifted in the direction toward lower magnetic field, causing chemical shift artifact. Well, there's a second type of chemical shift artifact, and that's when if there are two tissues with different magnetic susceptibilities and they're in the same voxel. Now, before we were talking about fat and water next to each other in different voxels, but now if they're in the same voxels, then the protons will precess at different frequencies. Initially, they'll be in phase, but then as time goes on, they'll go in and out of phase in what's kind of called a beat frequency. So at 1.5 Tesla, they go in and out of phase every 4.5 milliseconds. So at a TE of 0, they would be in phase. At a TE of 4.5 milliseconds, they're actually out of phase. At a TE of 9 milliseconds, they'll be back in phase, and that'll go on as you increase the TE time, and this happens twice as fast at 3 Tesla. So that then allows, if you can uh, uh, get images with low enough TEs, then you can get in phase and out of phase images. And you're all mostly used to that from your residency when you're looked at body images. A lot of people use in and out of phase images to look at the adrenals, because if you have a drop off of signal, a significant drop off, when you're in the out of phase versus the in phase, that means you have fat and water in the voxel. Tumors tend not to have fat in the voxel, and therefore, if you have chemical shift type 2 artifact, you're dealing with tissues with both fat and water, and therefore they're probably not tumorous. Whereas if you don't have fat in it, so you don't have type 2 chemical shift, then you have to be worried about neoplasm. And that actually also is very helpful in some bone tumors. So this just shows the beat frequency. If we have here protons and two different magnetic fields so that they're resonating at different frequencies, it turns out that they'll be in phase a part of the time, then they'll become out of phase, and then they'll go back into in phase. And if you have the same numbers of both of them, what you'll find is when you sample in phase, you'll have a lot of signal. When you sample out of phase, the signal will go to 0. So basically, if you have the same number of fat and water protons in a voxel, and you image at different TEs, you can see the signal going from everywhere from bright to no signal at all within that voxel. And that lets you know that you have both kinds of tissues in the same voxel. Now, the best way to do this in current technology is using ideal images, where we get in phase and out of phase images. And this just shows an example here where this is an in phased image where both fat and water add together and we don't see anything within the bone. But if we go to an out of phase image, here's an area where we have both water and fat, and we can see a dropout of signal. So here the fat and water added together and we see nothing. Here this area has granulation tissue in it, which is abnormal, and the water and the fat give equal amounts of signal, and then the out of phase TE, the signal goes to 0, and these turn out to be very sensitive for looking at areas of bone abnormality. This is probably even more sensitive than the STIR images in detecting this.
Is in phase just a normal T1, or
Now, typically when we do T1 weighted images, we're imaging with much longer TEs than this, and the in phase and out of phase really doesn't have much of an effect. You really need to go to shorter TEs. So it's usually either with gradient echo images, which is what you use in body imaging, where you can get short TEs, as short as possible to get an in phase and out of phase. So at 1.5, you'd like a TE of 4.5 and a TE of 9.0 milliseconds, and those would be the out of phase and in phase images. And they'd be shorter than that at 3T. And the shorter the TE, the better the signal to noise. So you try to do the short TEs to get the in phase and out of phase. Ideal is a more complex way of doing that. We'll talk a little bit about ideal later when we talk about different pulse sequences. This is a more sophisticated way of doing the same thing. Right? Okay, so we've talked now about localization. Now,